Okay, so we'll look at an example now for the application of the Newton-Cotes method. So this is the ODE that we want to solve, and it is subject to these conditions here. So we are asked to solve this ODE with h is equals to 1. Okay, so what you need to do first is to identify what these values mean. Okay, so at x equals to minus 1, we have y minus 1 to be minus 0.393. Okay, and for x is equals to 0, your y0 is 2. So we know the values of y at the previous two steps, which means if I'm going to write this out, your xi minus 1 would be minus 1, so your xi would be 0, such that your yi minus 1 is given by this and your yi is given by 2. Okay, so after you have done that, you write out your general equation. So you have your yi plus 1 is equals to yi minus n plus the integral from xi minus n to xi plus 1 fxy dx. Okay, alright, so you can see that the I minus n here, the n here is basically equals to 1, which means if I is equals to 0, then the first value of y1 would be y minus 1 plus xi minus n, so this would be xi minus 1 or x minus 1 up to x1. So that should be x minus 1. Okay, so our job now is basically to evaluate this integral. You can see because we know the value at x0 and one previous value at minus xi minus 1, that means we can use the rectangular rule. Okay, so the formula for a rectangular rule is basically 2h at fi. So if I replace this into my integral, what I get is my value of y1 for superscript 0 is given by y0, is given by y minus 1 plus 2hf at x0. Okay, so just sub in all the values that you have. So what is yi minus 1? Yi minus 1 is minus 0.393 plus 2h is 1, and the value of f at x0 is just the evaluation of this function at x0. Sorry, it shouldn't be x0, but it should be x0 y0. Okay, so what you have here eventually is you have 4 times the exponential of 0.80 because x0 is 0, so this will be minus 0.5 times your y0. So your y0 is given by 2. So the value that you get here is 5.607. Okay, so this value is not accurate because of the open Newton-Cotes formula. So what we want to do now is to apply the closed Newton-Cotes method to solve this. Because we have used the rectangular rule, this is of order h cubed, which means we want to apply the trapezoidal rule because it has the same order of accuracy. So what we can do right now is write the value of y1 for my corrected value. Okay, and this would be given by y0 plus half h f at x0 y0 plus f at x1 y10. Okay, so you can see this statement here basically calculates the new value of your y1. So if I'm going to plot the graph out, okay, let me use a bigger one. If this is your function f that you are integrating, so initially you have the value at x equals to minus 1, and then you have your x is equals to 0. So you're using these two values to find out what is the value of y at x equals to 1. Okay, so you're using this open Newton-Cotes formula based on these two values here to find out the value of y at x equals to 1. So once you have obtained an approximation, so let's say okay, if you apply the rectangular rule it goes something like this. So this would be your yi plus 1 for your first approximation. Okay, now when you do your closed Newton-Cotes method, what you're doing is you're basically using only this section here to apply your trapezoidal rule, which means when you write your equation, it'll be yi plus 1, sorry, it'll be y1, okay, is equals to y0 plus the integral which is given by the trapezoidal rule is half h f at x0 y0 plus f at x1 y1 0. Okay, so if you put in all the values here, so all these values should be known to you because you know your y1, which means you can calculate what is your f at x1 y1 0. So if you put all these values into this equation here, what you get in the end is y11 is given by 6.549331. If you compare this to the value that we have before for y10, we have 5.607. You can see that there is a huge difference. So you can apply the closed Newton-Cotes method again, but this time you just calculate f at x1 y11 to find out what this value is. So once you have that, you can use back the same equation, and that should give you a better approximation. So you keep on doing this until the value of your y1 in your two successive iteration is less than a certain tolerance. Okay. All right. If I go back to, okay, in your Newton-Cotes method, this step here is known as your predictor step. Okay, because you're actually trying to predict what is your value of y1, which is not known. So once you have obtained your y1 from your predictor step, you can apply your corrector step. Okay, so you can apply your corrector step here to find out what is the corrected values of your y1, and you can keep on doing this until, as I've just said, until the values of your y1 in two successive iterations is less than a certain tolerance. Okay, so once you have your y1, you can go on to your y20, and you can do back the same thing to find out what is your y2. All right. So the one thing that you need to remember is when you apply your Newton-Cotes method, the order of accuracy of your numerical integral that you use for your open method must be the same as your closed method.